Hi everyone, welcome to part 2 of week 12. I'm going to be discussing how to run t-tests and ANVOAs in R. So as I mentioned in part 1, and I'll reiterate now, I'm not going to be teaching you what is a t-test, what is an ANVOA, as statistics is a prereq for this course. I'm just going to be teaching you and going over how to run them in R. If you want some more information and a refresher in t-tests and ANVOAs, there is some information with the Word doc available this week, and there's also a nice link provided here that kind of goes over the differences between paired and unpaired t-tests and is kind of, concise and straightforward. So I'm going to be starting off with the most simple t-test, a student's t-test, then going through paired t-test, pairwise t-test, ANVOA, and then I'm going to talk a little bit about strings and dates. So getting started, looking at a student's t-test, we're going to use the command t.test. So pulling up the help page for this, we can see student's t-test and what are the arguments associated. At minimum, we have to provide x, which is a non-empty numeric vector of data values. So one column of your data set or one portion of your data set. This is a student's t-test, so we can see if we want to do a t-test of x equals 1 to 10, we're going to see if if the true mean is equal to 0 of the values 1 to 10. So here we're saying that x is the values of 1 to 10, run a t-test on it. And we can see that there is a statistically significant p-value associated with this, a p-value less than 0.05. And the mean of these data is 5.5. So we can see that the true mean is not equal to 0. That's the most basic, simple t-test that you can do. If you also want to run a t-test for 2 samples, this is going to turn it into a Welch's 2-sample t-test. So then you can provide both x and y. If you don't provide y, it's assuming y is null. It's going to run it as a student's t-test. If you provide y, then you're providing a second set of data that you're going to be running a t-test for, and it becomes a 2-sample t-test. So if we wanted to run a t-test, y is the values 7 to 20, x is the values 1 to 10. So x is 1 to 10, y is 7 to 20. As you can see here, if we look at x, if we look at y, we can either create these as variables and just do them as t-test xy, since these are now variables, or we can do t-test x equals 1 to 10, y equals the binding of c 7 to 20, or we can just do t-test 1 to 10, 7 to 20. So there are these 3 ways that you can write them, whichever you would like. So running this t-test of comparing our x to our y, we can see that we have a statistically significant p-value associated with the differences between these 2 samples. It's a Welch's 2-sample t-test, which is different than our 1-sample t-test, our student's t-test. And these p-values statistically significant, and the mean of x is 5.5, the mean of y is 13.5, and there's enough information that the true difference in means is not equal to 0. If we were to run x as 1 to 10 and y as 7 to 20 with an additional value of 200 added at the end and rerun this t-test, we can see that this creates a big difference in our confidence intervals. It was -4 to -11. Now it's 6 to -47. Our means are different. Our t-value, degrees of freedom are different, and we are no longer statistically significant. So we have changed the distribution of these data. We have added this 200 here. Our variance is different, and our confidence interval is different, and we are no longer certain that the difference in means is not equal to 0. So this is statistics information. Once again, I'm really just showing you how to run a student's t-test, Welch's 2-sample t-test. So if we were to look not just at these numbers that we're putting in, but actually a data set, once again, I'm going to look at the data set iris, which is based on the flowers and the sepal length, sepal width. So if we wanted to run a student's t-test on iris, we would need to pick what column, what one sample set we want to run. So if you recall from part 1 of the lecture, there are multiple ways to choose your column. You can either do the brackets with the column name in parentheses. You can do the coordinates where it's rows and columns, or you can do the $sign. So first, if we wanted to do a t-test of the petal width column, which is this 4th column here, we can just run it like this. We can see p-value is statistically significant. It's a one sample t-test. We can get the mean. And this is the exact same as if we were running iris petal width. As you can see, once again, I type in the $sign, it gives me all the possible options. So the exact same values, I'm running the exact same thing. When we look at iris, we can see that in the last column, iris species, there are 3 different species that we're looking at. So if we wanted to look at only a subset of the data, only one species of iris, we can pull out just one of the species and run a t-test on that. So part 1 went kind of over how to subset data. Well, it did go over how to subset data, and here, once again, we're seeing that in action. So I'm going to take iris rows 1 to 50 and all columns, which are all of this Setosa species. And I'm going to name this as a new variable data set called iris Setosa. So now iris Setosa is just the first 50 lines of this data set. And I can run a t-test on just iris Setosa petal width column. And so now I'm getting, now I'm testing for differences in petal width for just the one species. As a note, if I were to run t-test iris Setosa and try to run a t-test, you're going to get an error. So you can either Google this error, you can read what the error is saying. A lot of times it's kind of confusing, or you can kind of look at what mistakes you might have made by looking at the help page. So what a t-test is looking at one column or 2 columns. Here, iris Setosa is a 5-column data set. So it doesn't know how to run a t-test on a 5-column data set. And so you have to select your specific column to run your t-test on. So even if you've subsetted the data, if your data have more than 1 column remaining, you need to provide information about what column you want to run. Now, if you were to do iris 1 column, and you were to just look at iris column 3, and you were to make this a new data set. So now you have iris 1 column. You can see that it's just 1 column of 150 rows of data. And if you were to test now a t-test on iris 1 column, you can see that it'll run, because even though you're still running an entire data set, your entire data set is just 1 column. Okay. Then if we were to look at the other data sets available, such as cars and MT cars, we can see that we can run the one sample t-test on any of the columns as long as there's numbers in those columns. As a reminder, you can use the $sign to call out specific columns. It's probably the easiest and least confusing, especially since as you are typing the $sign, it gives you all of your possible suggestions of what you can type. So we can run a t-test of, multiple columns in iris, in cars, in MT cars, and we can run a t-test on just specific columns in NT cars using the $sign or using numbers. We're going to get the exact same value. So the first column in MT cars is MPG. We can see that we're getting the exact same data if we're running it as MPG called out with a $sign or MPG called out with a select the first column notation. Okay, that's the basic student's t-test, a little bit of an intro to Welch's 2-sample t-test. Your command is going to be t.test. You can find more information on the help page here. Make sure that you're only feeding in one column at a time, either by calling it out specifically here or by creating a new variable data set. When you're using the t.test command, be careful when you're choosing your groups. Make sure that what you're running as your X and what you're running as your Y are what you're hoping to be running. So inherently, when you're running a t-test with an X and Y value, it is saying that your paired is false. These are not paired samples. These are independent of one another. We're just looking at the differences between those two columns of data. So paired is assumed to be false. So if you run iris sample length as X, iris petal length as Y, and write paired equals false, you're going to get the exact same as if you didn't include pair equals false, because that's what its null value is. That's what it's assumed to be. These values are the exact same. If you were, however, to change paired equals true, and as a note, remember true is uppercase letters. If you were to run pair equals true, it's going to change what it's running. So now we are running a paired t-test. Before we were running a Welch's two-sample t-test. Now we're running a paired t-test. We're saying that iris sepal length and iris petal length are paired. It's a paired set of testing. They are dependent on one another, or they are related to one another. Run this as a paired t-test. Now we are not getting the mean of X and the mean of Y. We are getting the mean of differences. So check up on your data. If you don't know what a paired t-tests are, Google it, go over the Word document this week, use the link at the top of this. But to run a paired t-test, you change pair is equal to true. So once again, running a paired t-test, we are looking at X and Y as paired values. So sepal length and sepal width as an X and a Y. And we are looking at the difference between XY and XY between samples, not the difference of X and the difference of Y. So paired t-test is different than a Welch's two-sample t-test. Welch's two-sample t-test is looking at the X mean and the Y mean. So this is as much as I'm going to explain about the difference between those. Moving on, we can also do a pairwise t-test for multiple paired t-tests across a group. So it is not a paired t-test. A pairwise t-test is multiple pairwise analyses. So instead of just looking at the mean of the differences, we are doing multiple pairwise analyses. So if we were to look at the built-in dataset sleep, and we were to look at the pairwise t-test of extra and group, we can run pairwise.t-test. So instead of just t-test, we've added pairwise dot in front of it. And we're going to run sleep extra as X and sleep group as Y. So we can see if we run this, we're going to get a pairwise comparison of the sleep extra column and the sleep group column. For pairwise comparisons, you have to tell it your p-value adjustment method out of several methods. If you do not tell it a p-value adjustment method, it chooses home. That's fine. Just leave it. I don't care about your p-value adjustment method. This is not a statistics class. Just leave it. But you can see if we would go to pairwise.t-test help page, the p-adjust methods is one of the arguments. You can read more about p-adjust methods here. Just stick with home. That's absolutely okay. If we were to look at sleep extra and sleep ID instead of group as a pairwise t-test, you can see that sleep group has only two factors. You're either in group 1 or you're in group 2. That's why the pairwise comparisons here and the p-values listed here, this is the p-value that it's computing. It's just the simple one because there's only 2 groups. If you were to look at sleep IDs, there are 10 different groups. So it's running multiple pairwise analysis for all of the sleep extra data points and all of the sleep ID data points as a pairwise analysis. So it's giving you your p-values for all of those comparisons that it's able to do. I don't think many of you are going to do a pairwise t-test. I think you're going to do a paired t-test or a Welch's two-sample t-test, but I want to to teach you how to do a pairwise t-test just in case. You can, if you wanted to rename your p-adjust method, which I don't think you need to do, I am not looking at it in your final project. I'm not going to be checking what p-adjustment method you did. You would use the argument p.adjust.method equals home. And the different methods are home, Hochberg, Hamel, Bonferroni, Ferroni, BH, BY, FDR, and none. Don't worry about them. If you want more information, I've linked something here. Just leave it as nothing as up in these. But if you wanted to ingest it just for fun, go for it. Okay, so we can also run a pairwise t-test. Here I was using sleep. Here I can use the iris data set. It's my favorite. That's why I use it all the time. A pairwise t-test between sepal length and iris species. And we can see that it's looking at the 3 different species as pairwise comparisons. So the species difference of sepal length between setosa and varascolar is statistically significant. Varascolar, we can't compare. Varascolar versus virginica, statistically significant. Setosa versus virginica, statistically significant. But we've pulled it out, and now we have comparisons based on the species-wise comparisons. So I think pairwise t-testing can be helpful, especially if you have something like species or states. But just remember that it's doing multiple pairwise comparisons, unlike a t-test, which is comparing your pairs. We can also use something in R that's for formulas and relationships, and it uses this little squiggly line here that we use a lot in engineering to be about. So this is a formula. You can look at the formula help page where it kind of goes over what are some of the formulas available. I don't find this help page very useful, but it might be helpful for you. And one of the ways that we use formulas is to indicate a relationship. So you can use the squiggly symbol to indicate a relationship. The formula means I want you to look at this within relation to this. I'm giving R the fact that there's a relationship there. So there's a command aggregate, which aggregate means like group together. So if we look at the help page for aggregate, and then I want the one in the stats library. Aggregate is you have to provide one X. That's all you have to provide in terms of argument. X has to be an R object, and you're telling it what you want to aggregate and how you want to aggregate it by. So it's essentially like a grouping command. If we want to aggregate something in iris, we can do that using the aggregate function. Okay, so we're looking at iris, and here I'm going to aggregate petal width by sepal width in the data set of iris, and I'm going to aggregate by mean. So I'm going to group petal width by sepal width in the data set iris, and I'm going to group them by the mean. So I would copy this and type in your own data set for this. Don't worry about understanding too much of formulas. This is a really basic intro, and we're just looking at grouping a set of data by another set of data using mean. So you can see when I run this, I'm grouping sepal width with respect to petal width by mean. So now sepal width are in order, petal width are grouped corresponding to the sepal width by their mean values. As another example, we can do aggregation by their median values. So instead of their means, which, 1.33, 1, we're going to get 1 and 1.5. They're median values. But we're still grouping this petal width by sepal width based on its median value. So we're grouping by median provided here, and we're grouping sepal width, this Y value, with respect to this X value. So the petal width is what we're getting the median of and mean and grouping. We can also look at US arrests, and using the US arrest data set, we want to group by mean all of the urban population values. We want to group murder by urban population in the US arrest data set, and we want them to be grouped by mean. So here we have urban population, that we're looking at urban population in order. So we have 32 in order to 91. So we've arranged these, and then we've grouped them with murder based on the mean value for murder. So I think you'll understand this a little bit more when you mess around with it. It can be really helpful for putting your data in order if that's something you need to do, and grouping certain parts of your data. I believe we can also just aggregate without using a formula. We can aggregate petal width data equals iris by mean. Oh, I need to tell it where this petal width is from. No, it doesn't like that. All right, so maybe aggregate will only work if you're putting it in relation to things. Or maybe, so it looks like, yeah, you need to use the formula when you're using aggregate. So this wouldn't work. Need formula to use aggregate. Okay, another example is you can use this sorting function. So I want to group petal width by sepal width using the mean value. So you can run this as a new aggregate, but then if you name it, you can create it as a new data set. So now I can do a t-test of this aggregated data. And so it's order, you're now doing a t-test of the mean value of your petal width grouped in order by sepal width. And so you're running a t-test on kind of a more concise group of data. And this becomes a one sample t-test because you're running your one sample t-test of your iris mean value, and you're only running your t-test on like this data set. Okay. And it's assuming all of these are the data that it's running a t-test. It's not running these as paired. Remember, paired is assumed to be false. We can also use it with the, I'm just providing more examples. So the MT cars data set, we could do group miles per gallon by cylinder using mean. So now we're gonna have the different cylinder values and the averages of the mean. So you can see all of these cars either have 4, 6, or 8 cylinder. So I want to group based on their cylinders and average their MPG. Once again, we can do it with sleep, where I want to group their extra hours of sleep by their group. This one should only give us 2 values since there's only 2 groups. I want to group them by their mean. So yeah, there are 2 groups. You can kind of get their average extra hours of sleep. So if you wanted to run a t-test on this aggregate, now you're running a t-test on their average. Oh, it doesn't like that. Okay, let's see. Sleep ag. I'm going to rename this, and then I'm going to have sleep ag. Extra. So what happened here was I aggregated the extra hours of sleep by their group based on their mean. As you can see, their groups are either 1 or 2. Their extra hours of sleep were aggregated based on their mean values. So group 1 had an average of 0.75 extra hours of sleep, and group 2 had an average of 2.33 extra hours of sleep. So if I wanted to see if these were statistically significantly different from each other, I could run a t-test. So I had first said, okay, I want to run a t-test on these data. So t-test sleep ag, which is which are these data, right? Sleep ag is just this data set. I renamed it as a variable. When I run a t-test, it says your argument is not numerical or logical. It's saying I can't do this. So I had to figure out what I was doing. And I realized that I wasn't giving it the specific column that I wanted a t-test on. So then I had to tell it I want a t-test of extra. Are these significantly different from one another? So it says, no, not really. So at the end of the day, the groups are not getting a statistically significant different amount of sleep from one another based on this t-test I just ran. You can even easier use formulas directly in your t-test command. So running a t-test, you want to see the t-test with the relationship between extra hours of sleep and their sleep group. So essentially the exact same thing that I'm running here, but you can run it with the formula right in the t-test command. So I'm getting the mean of group 1 is 0.75, which is what my aggregate data was telling me. The mean of group 2 is 2.33, which is what my aggregate data was telling me. And then here it's telling me that this is statistically significant. So as you remember from statistics, here I gave it 2 numbers and said, are these different? But down here, I gave it this entire set of numbers and asked, are these different? And they said, yes. I didn't tell them that they were paired. That's why it's a Welch's 2-stable t-test. But I did tell them, I want to run this in relationship to this and test these two. You can also, you have to tell the t-test what data you want to use if you're not using the $sign, but you could just use their column headers and then tell them data equals this. But if you want to do a t-test with a formula like this, just a basic t-test, not a paired t-test, not anything, you have to have a binary factor as your Y value. So your group here is either group 1 or group 2. This has 2 levels. If I look at switching these around, so now I'm running a t-test of the groups in relation to their extra hours of sleep, it tells me grouping factor must have 2 levels. So now my grouping factor not only is not binary, which is 2 levels, but I was using it as my X value instead of my Y value. So you need to use this exact nomenclature if you want to use it like this, and you need to have your group here be binary. Is it on or is it off? Is it yes or is it no? Is it 1 or is it 2? But if you wanted to, if you want to look at the relationship between multiple columns, you need to either use a pairwise t-test, paired t-test, or an ANVOA. So this t-test command is just for really basic t-tests where you can also include a binary factor as in your formula as your relationship here. Okay, this is a little complex. I think some of you might be interested in doing it, but for most of you, I would stick to the basic t-test, paired, t-test, unpaired, pairwise t-test, and not doing formulas or aggregates. Moving on to an ANVOA, or an analysis of variance, a t-test is looking at the differences between 2 groups. They can either be 2 groups that are paired, 2 groups that are distinct, or looking at 2 groups across multiple comparisons. An ANVOA can look across 3 groups. So if we're going to do an analysis of variance, we're using the command AOV, which is a formula for fitting data using an analysis of variance statistical analysis. And this is exactly why we're using R, because R has these commands, unlike a lot of other coding languages. It can run more powerful statistical analysis, such as fitting data to an ANVOA. So if we're looking at cars, which is one of the groups built-in data sets, and we want to run an analysis of variance on the data cars. So first I'm going to look at the help page for the analysis of variance. You can see what you have to provide. You have to provide first a formula, which we use by that squiggly line. I just went over this. And then we have to tell it what data we're using. So if we're looking at cars, we only have 2 data points, so it's easy to come up with a formula. We want to look at speed as in relation to distance of the data set cars. So we want to have an analysis of variance of speed across distance in this data set. So we can see now the sum of squares, the degrees of freedom, the residual error. These are all statistical information. And it says estimated effects may be unbalanced. So it's giving you information about this analysis of variance fit. And we can save this as a variable, and we'll get the same thing if we look at the variable. And then there's a helpful command called summary. So now we can look at the summary of our analysis. And this provides us a little more information where we're getting our degrees of freedom, our sum of squares, our mean squared, our F value, and our PR value. And then our significant codes down here at the bottom. These significant codes kind of show you if your values are significant or not. So if it is close to 0, you get 3 stars, which is 10 to the minus 12. This is related to your p-value here. If you are at no stars, no asterisks, then it's not significant. So it's just helping you, giving you a little bit of a hint if it's considered significant or not. So we can also compute the analysis of variance on MT cars. Here we have more than just 2 variables. So we would want to figure out what we want to look at. Do we want to look at miles per gallon in relationship to cylinders, or in relationship to horsepower or weight of the car? All of these might affect miles per gallon. So you have to figure out what exact questions you're asking of your data. So here I want to look at miles per gallon in terms of horsepower. So miles per gallon in relation to horsepower on data MT cars. So I can run this analysis of variance, I can look at the analysis of variance, and then I can check the summary. So I can see that there is a statistically significant difference between across miles per gallon as a function of horsepower. I can also look at MPG across weight instead of horsepower. And I can see, once again, I'm getting a significant difference. So here we're not, this is a fit of an analysis of variance model. So here we are asking for the analysis of the variance. So how much do these values differ in respect to one another? When we are looking at these with these formulas, we're saying MPG with respect to weight, do they change across samples? And it's saying, yes, they do. We can also run this with iris, my favorite data set. We can look at sepal length with respect to sepal width. And we can see that this is not statistically significant. So they don't change over time or across samples. So it doesn't change across samples or across time significantly. We can also look at sleep. So we want to look at extra hours of sleep by group and do an analysis. We can see that this is not statistically significant. There are no asterisks. So we're saying that the amount of extra sleep did not significantly vary across groups. Along with this analysis of variance AOV, you can also use the code command ANVOA. But ANVOA, you have to give an analysis of variance fit or another fit object. So you can't just type in your data set to this command. You have to type in your analysis of variance data set. So here we can run ANVOA on our MT cars analysis of variance that was run up here. And we can see that we're getting statistically significant values again. So if we were to run just our MT cars analysis of variance and look at the summary, we can see that the summary of our analysis of variance fit model and our MT-cars are giving us almost exactly the same values. So ANOVA is giving us a little more information, 847.7, 847.73. So we're getting a little more precise and a little more information here, but overall it's going to be just another way of running an ANOVA. We can use other models besides AOV, which is an analysis of variance fitted model. We could use linear fit if your data are linear or close to linear. And the way that we use linear is by LM. So for most of you, I would look at AOV, just assume AOV. But for those of you who are interested and those of you who want another way of doing it or have very linear data, we can use LM as a model for linear fit. So instead of having AOV, we would have LM. So ANOVA, I want to run an ANOVA of a linear fit model of data sleep extra column with relation to group. You can see running this, it gives me an analysis of variance table, which is going to be different or might be different depending on if we have linear data or not, from if we were to run the same thing with the command of AOV fit model instead of a linear fit model. So we can see here that actually our responses are the same, which means that we likely do have, I believe, close to linear data. I don't need you to know exactly if your data are linear, if they can be approximated as linear. So I wouldn't worry too much about this, but this is another way of running a fit within your ANOVA. And we can do this for MT cars, with iris, and with cars. And we can choose what sort of arguments we're adding as our formula and as our relationship. We can also use t.test as an ANOVA test with no assumption of equal variance. So this is variances, and the assumption of equal variances is from stats with ANOVA. But we can use this command test to look at how our sleep data are varying as group, as with extra sleep across the group. We can run this as one-way analysis of means, assuming no equal variance. So this is very similar to an ANOVA, but it's a little more simple and it's not assuming equal variance. We can assume that the variances are equal by changing very equal to true. And we can see that when we are assuming that our variances are equal, we're getting kind of similar values, but they are different. So if you know for sure your variances are equal, or you did a variance test before, remember the command var, we can, right here, we can use this one-way test, one-way.test. Okay, so commands that are helpful for running t-test. Commands, t.test. Pairwise, t.test. AOV. ANOVA, but you have to have an AOV or an LM inside. And then one-way.test. So I'm expecting you to look at your data, look at the values you're getting, look at what's giving you as statistically significant, look at what you want to test, and spend time figuring out what variables you want to test with in relation to one another, what variables you want in this formula. And then you can use these commands for running t-test or running ANOVA. As a reminder, you can have t-test where paired is equal to true or paired is equal to false. So it's assuming that your paired value is false unless you tell it otherwise. And if you tell it otherwise, then you are running a paired t-test. Okay, I want to move on to strings. So I mentioned last week or the week before that strings are something that I would touch on later, and now I am. So strings are anything that are in quotations. Typically we treat them as words, but Not exactly. So they're called strings. When you're inputting data, sometimes you might want to have strings considered to be factors, which are kind of like groups, right? So your factor is either, today, tomorrow, or yesterday. And so those are strings, right? The word today. The word today in parentheses is going to be a string, but you can also have this count as a factor where it's kind of creating like a bin or an area that is not considered just a word, but a different level or a different factor. So sometimes it's helpful to have strings read as factors. Sometimes it doesn't really matter. I'm not going to expect you to know too much about strings for this class, so don't worry too much. But just know that strings are anything that are in parentheses. If we look at USARS, if we look at this data frame, and we look at row names in this data frame, we can see that these are all in parentheses. I'm sorry, quotation marks. These are all strings. So if we were to create a variable of just these state names, they're all strings. If we wanted to make them into factors, so different factors, we can use the command as factor. And then we can see that these are no longer in quotation marks. These are now factors, and we have 50 different factors. So if you have multiple states with multiple data points, sometimes it's nice to have them as factors because then you can group them together using aggregate. You can also change the way strings are displayed by using this substring command here. So if we were to look again at states, we can change the way that our substrings are, or our states are being displayed. So here they're displayed as full names, but we can say that we only want the first and second letter of these strings. So I want you to start at letter 1 and end at letter 2. If I started at letter 1 and ended at letter 4, I would get the first 4 letters. If I started at letter 4 and ended at letter 8, I would get the middle 4 to 8 letters. So that's how you can subset and change the way your strings are being displayed. Sometimes you can also use this command string to integer. So if for some reason you have a number that is as a string, you can change the string to integer using string to integer command. So for instance, I want to change this string of quote 1 into an actual integer as 1. So this changes to integer or a number. You can also use the as numeric or as integer commands that are just as helpful. So string to integer or as numeric will also give you 1 as a number, or as integer will give you your string as a number. We don't want to do this on like full strings as in like states, but it's easy to do if maybe a couple of numbers got messed up. Okay, so if we look at iris species, we can see that there are 3 species. They are not in quotations. And if we check the mode, we can see that these are considered to be numeric, even though these are words. So sometimes it's helpful to have these as numeric or as factors because it allows you to group them and look at them as a little more integral to your data than just headers or comments. If we try to make as numeric to something that's already a numeric, then it gives it to us in factors. So it tells me that iris species is already a numeric, but when I ask it to make it a numeric, it creates it as either 1, 2, or 3, and assigns all the species of Setosa to 1, all the species of Versicolor to 2, all the species of Veronica to 3. There are a lot more things you can do with strings. You don't need to know them. Just basically know what strings are and a general idea. I know several of you have dates in your data set, so R can be very particular about dates. I've linked a couple of links here that can help you. I'm just going to briefly go into it. There's a command called as date, and the date is capital. So we can see that it converts a character, so something in quotations, to a date. And then you can use R to look at dates. Please email me if you are using dates or you want to use dates. I can help you. I don't want to spend too much time on it because I'm not sure how helpful it will be and it gets kind of complicated. So please email me or Dr. K if you have questions about dates. But in general, the command as date will change you can either subset part of your column that has dates, or you can use this example that's just looking at a character with dates, and it will convert this into a date. So it's now considering this to be a date. And it does this for multiple different formats. You can tell it how you want it to be formatted, month, day, year, and it gives you that information in as date down here. So you can change the way it's formatted as a date. You can also change dates from characters. Here they still have the quotations. They're still strings or characters. And you can change them to a numeric, even though you aren't getting a number that is 1999 to 17. You're getting a number that is the numeric representation of that date. If you were to try to run it without telling R that this is a date, it says, I can't do that. NA's introduced by force. So you have to still tell it that you want as numeric of as a date of a certain date. So 2/20, 1990. And then, oops. Oh, okay. So it's telling me that it doesn't like this format. So character string is not in a standard unambiguous format. So there are even like specific ways that it wants date. It still doesn't like that one, but it should. Maybe I have to tell it its format here since it doesn't. There we go. Okay. So if you're getting this error as it's in an unambiguous format, you have to tell it what format you're using. And then you can run this as a date and get your numeric. So I can help you with dates. This is just a brief introduction to dates. R is very particular to dates. So either use these links, use kind of this intro knowledge, or email us or Google it. Okay, so for the assignment this week, I want you to run either a t-test or an ANVOA on your data using the commands and the subsetting that we've done in these last two videos. I hope I've given you a lot of resources. These videos are long and very in-depth, and please email us with any questions or clarification, and I hope you have a great week. Thanks.